Hi, it's me, Tim Dodd, the Everyday Astronaut. I'm at a random Airbnb here on the Space Coast waiting for the first crewed Starliner launch, but I just had the opportunity to catch up with the crew of Polaris Dawn and talk about the incredible EVA, or extravehicular activity suits, that they just revealed with SpaceX. Now, although these may look very similar to the standard SpaceX spacesuits, the IVA suits, or the intravehicular activity suits, they're actually basically entirely brand new, which is something that I learned in this conversation. And these spacesuits are going to allow them to do the first ever commercial spacewalk. This mission has a ton of incredible science, and it's a really complicated mission profile that we talk a lot about in this conversation. So without further ado, let's hear from them. Why don't you guys just introduce yourselves, and then we'll get into some awesome questions to learn more about your mission.
Hi, everybody. My name is Sarah Gillis, and I am both an engineer at SpaceX, as well as one of the mission specialists on the Polaris Dawn mission.
Great. Hey, everyone. Jared Isaacman, Commander Polaris Dawn.
Kid Poteet, mission pilot, Air Force background, 20 years F-16s.
Hey everyone, I am Anna Menon, and I am also one of the mission specialists on this mission, as well as the medical officer and a SpaceX engineer.
Awesome. Okay, so first off, let's do, because it's maybe been a little bit for some people to remember, your mission profile is quite different from anything flown really since the Gemini era, frankly, and very different even than from Jared, what you did with Inspiration 4. Just run us through the mission profile of orbits and all that stuff of where is Polaris going?
Yeah, sure. So, I mean, you said it right. I mean, Inspiration 4 was just about showing that, that it could be done. Sending a very inspiring message about what our future could look like in space, and also the, things that we could accomplish here on Earth. We always said if Inspiration 4 went well, there'd be a lot of exciting missions to follow, and there have been. You see it with Axiom, and the Polaris program is just another, great example of that. So we named it Polaris after our North Star, which is a constellation of 3 stars, for those who aren't familiar. Polaris program contemplates up to 3 missions, the third mission being the first crewed flight of Starship, and the first mission, which is what's approaching very, very soon, is Polaris Dawn. And we've got some pretty awesome objectives. So we'll launch in a 190 by 1,200 kilometer orbit. That's where the second stage will drop us off. From there, we'll do a bunch of system checkouts. We'll raise our orbit up to 1,400 kilometers. So that'll be the farthest we've gone from the Earth since the last time humans walked on the moon with Apollo 17. There's a lot we stand to learn from that with between our slate of science and research experiments, vehicle architecture. Avionics generally don't like radiation. We should learn from that. And then we'll come down to our cruise orbit, which is 190 by 700 kilometers. We'll vent our vehicle down and we'll conduct a spacewalk. And we're going to test out a brand new spacesuit. This is super important. EVA suits have not really evolved much in the last 40 years. They're incredibly expensive. And they're nothing, as you know, like the movies of just throwing on your helmet and running outside to explore the planet. And SpaceX wants to move in that direction, especially if we imagine a future with lots of people on the moon and Mars someday. So we're going to test out our new spacesuit. We're going to communicate over, Starlinks over a beam of light, which is pretty cool. We got a very exciting message send in that regard. And then about 40 science and research experiments. So an awful lot to accomplish.
Okay, there's so much to just unpack from that little quip there. So let's start off at the end there. You talk about Starlink. Is this the first time that a Dragon capsule will officially use Starlink as probably your primary source of data, uplink and downlink? Is this the first time?
Yeah, it would be the first test of Starlink from space. And just to amplify, as Jared mentioned, this is a developmental program. But we also want to make sure that we're doing the right thing with planet Earth and improving life. And that's exactly what SpaceX is doing with Starlink capability with laser communication. We got to see it firsthand with our collaboration with St. Jude. They brought us to the Philippines for us to deliver Starlink units. And what we witnessed was the ability of families in remote locations to be able to communicate with hospitals and get the care that their children needed who were fighting cancers or life-threatening diseases. So it's bringing a capability that's completely changing the way we communicate, specifically for these remote locations. Telemedicine, treatment procedures, education, because they'll require long-term care at some of these facilities. They got to get an education. They got to be able to communicate with family back home. So really important research that is more or less changing globally how we communicate. And so we just want to continue that evolution of communication, and it's really important for us to use Starlink for these longer duration missions. You know, the broadband is better, the latency is less, and it's going to be the first time that it's been done from space. Modifications done to the capsule, to the trunk to be able to communicate. You know, we're traveling 17,500 miles an hour. These satellites are traveling the same speed. Trying to link those two up is no short of a miracle, and that's what SpaceX has been working on.
And is this one of the first times, too, that Starlink's going up instead of down? Because normally it's obviously linking to Earth, but you know, I don't know if we have ever really had a chance to see them operate in that inverse direction.
Yeah, I think it's super exciting. Just envisioning the Starlink constellation, we're going to be both orbiting above and below it on every revolution. And so you're basically having to direct a laser beam at the trunk of the spacecraft to send data to the spacecraft, and then inversely pointing a laser beam that's attached to Dragon back at the closest Starlink as you're passing over it. So incredibly complex technical challenge. The SpaceX team has been working really hard to make this a possibility. And I know because you care about the details, I just want to make sure what is specific in what you said. You know, we're testing out this capability. It is the first demonstration of this. It won't be the primary means of communication for our spacecraft.
Right.
So we absolutely hope to send you know, some really hopefully inspiring messages down to the Earth while we're up there. But it is absolutely a test demonstration of this technology.
You're right. That's absolutely a good clarification. And in my head, I was thinking it's by far the most bandwidth that you'd be able to get to and from it. Yeah, and you're absolutely right. It's still not your primary means of communication, especially not on a first go like this. That would probably not be too wise. But now talking about orbit, I didn't realize now that you say it out loud, it's obvious. You're flying below the shelf of Starlinks and then back up again above. What's that look like as far as just trajectory and avoidance? And how do you know that there's, even when you do that in an airplane or a jet, as all of you know with all your flying experience, how do you avoid Starlinks and know that your path is clear and all that stuff? What's that look like?
Yeah, I think frankly, the work that SpaceX is doing for debris avoidance overall and, building out that capability to ensure we have safe space flight overall is incredibly impressive. And one of the things I think is really cool about this mission is actually SpaceX will have knowledge of Dragon's location. And so satellites can actually avoid Dragon preemptively throughout the mission. So it's just a really cool integration of technology across the spacecraft and this entire constellation of satellites for our mission.
So there might be some active avoidance almost between all systems. Starlink's kind of changing their orbits a tiny bit to make a little more room, make those margins safe, and also Dragon, does it have to do maybe a little maneuver at apogee or something to help avoid, or what's it actually look like?
There's a lot of space out there, and only about 5,000 satellites. So I think odds are pretty good that we won't have to worry about any avoidance maneuvers with known objects. I think it's right. When you start talking about greater than 1,000 kilometers, there's a lot of debris up there. A lot from like old ASAT tests and communication satellite parts and such. Like that's what you're way more worried about. Not intelligent Starlinks that can self-deconflict. It's the those really small but very painful objects that you can't track. That's the bigger concern.
Yeah. Okay, now before we get totally into suit land here, because obviously that's the exciting buzz for now, I've got a kind of more medical stuff, I guess, for Anna. What's it look like as far as you guys are going up to 1,400 kilometers? You're starting to get into a lot higher radiation portions. You're starting to kind of get into those outer regions, the Van Allen radiation belts. What's that actually look like on your mission planning, and how are you tracking radiation? What types of things are you doing to avoid or I guess reduce the exposure to radiation, or I guess what's it all look like on the medical side of things?
Yeah, so we are, as Jared alluded to earlier, doing a ton of research on this mission, over 40 science and research experiments over the course of the 5 days. And some of those are specifically targeting this higher radiation environment. And so to give some examples, there are historically mentions of astronauts seeing light flashes that are correlated with radiation or believed to be associated with radiation. So we will be doing some analysis and tracking of those sorts of human experiences in that higher radiation environment. We will also be testing out, doing a tech demonstration of a concept that utilizes a camera in that higher radiation environment to attempt a first X-ray in that environment, essentially harnessing that higher radiation to see if you can get this really mobile X-ray machine making use of the space you're in. And so these are just a couple examples of how we are attempting to really learn while we are up there, and then be able to take that knowledge back and improve future astronauts' lives, future missions that we're all excited about. But in terms of the medical implications, the dose of radiation that we anticipate receiving over the course of our 5 days is approximately equivalent to about 2 to 3 months on the International Space Station. So, well within human physiological limits, sufficiently safe, and we will learn a lot from it.
And that's probably mostly due to the part that, yes, you're reaching those high orbits of 1400, but that's at your apogee, and then you're coming back down. So you'll receive some amount of exposure, and then it goes lower and lower. So it's not like you're spending 5 days fully at 1400 kilometers. Is that kind of correct?
Absolutely. Exactly.
Yeah, and in fact, if just given your more technical interest, in fact, the vast majority of the radiation exposure will not even be at peak apogee of 1400, but the first 2 orbits at 1200 kilometers do go through the South Atlantic anomaly, which those 2 passes are your 2 to 3 months of ISS exposure right there.
Wow. And this has probably never really been done like this, where it's almost intentional to fly a flight plan where you kind of know there is increased exposure levels, and it leads to a lot of potential for science. But yeah, it's funny. I think people always get this fear of there's huge radiation levels, but they forget that it's cumulative exposure, and that you guys are kind of passing through portions for kind of a set time. Between that and then also we'll kind of get into the spacesuit now here, we'll transition between the radiation exposure, but also the way you're going to depressurize the entire spacecraft and have to then repressurize it eventually. Did those 2 things feed into your mission planning and actually your profile that you're flying? Like, how much did those 2 things, I guess, play into that?
Yeah, I think kind of as we've talked about, we'll start out in the 1,200 kilometer orbit, get through the South Atlantic anomaly passes, then raise our orbit and really get the data, collect the data, and then lower ourselves down to about a 700 kilometer orbit that will be the cruise orbit for the rest of our mission. And you're very correct that depending on where you're at in your orbit, when you're super low, you have all the protections of the Earth. You have your magnetic field that's helping you shield you from radiation. You have many fewer particles, for instance, debris that will just deorbit into Earth. So we will be lowering our orbit then and proceeding with the spacewalk. To kind of paint the picture for the spacewalk, we will all start by getting suited up in the suits that were announced so recently. We'll pressurize all 4 crew members in the suits on 100% oxygen before depressurizing the spacecraft. What's unique, though, is the preparation for this actually starts almost an hour onto orbit. So kind of as Jared alluded to, you can't just put on a spacesuit and go out at a much lower pressure without, decompression sickness risk, for instance. And so on our mission, we're actually doing a really novel pre-breathe protocol where over the first 45 hours of the mission, we are slowly decreasing cabin pressure and raising oxygen concentration. And that allows you to do a gradual removal of nitrogen from the tissues so that by the time you're at that 700 kilometer orbit, we're 45 plus hours into the flight, we are at a much lower cabin pressure to start. And so the difference between that cabin pressure and then our suit pressure is much smaller. And you can, you think of a can of soda, you want to basically, when you open it, you want none of the bubbles to come out, is the point of like saturating or removing nitrogen from your system. And so that's kind of the profile that we're looking at for this mission by the time we're ready to go and vent the spacecraft.
So can you remind me again, the numbers, like what is the base pressure and mixture ratio of Dragon on normal operations, and then how low are you trying to get it? And you are getting it all the way down to a pure oxygen environment in Dragon, is that correct?
So usually we operate at a standard atmosphere, 14.1-ish or 14.1 to 14.5 at 21% oxygen. For our mission, by the end, we'll be around 8.5 psi with maybe around 32% oxygen. Not sure on those exact precise final numbers right now. And then our suit, when we start pressurizing, we'll go on 100% oxygen for a fixed duration before we start venting the spacecraft. So we're not getting to 100% oxygen in the spacecraft, but we are getting it in our suits and pressurized on our person before we then proceed with depressurizing the spacecraft and opening the hatch.
So this is where things get quite different. And correct me if I'm wrong, I can't think of another time that 4 humans have all been exposed to the vacuum of space at the same time. Is that correct? Because even though there'll only be at first one person at a time doing a technical EVA, the hatch is open. You all are essentially doing an EVA. You're just doing an IVA EVA. Like you're inside the spacecraft. The spacecraft is exposed. It's in the environment of space.
Absolutely. We are all going on this spacewalk. And when you think about what's required to do that, the SpaceX for the last 2 years has been working on how do you safely take a spacecraft to vacuum, because it wasn't designed to do this under nominal operation. So it's been an immense amount of development by the SpaceX team. You have to add a nitrogen repressurization system. You have to ensure every material on the inside of the vehicle is compatible with vacuum and is not going to off-gas in ways that we aren't planning for. You have to add mobility aids to the inside of the spacecraft to ensure the pressurized suits are able to interface with the environment and move safely and successfully. So it's been really fun for us over the last 2 years to be working with the SpaceX team, iteratively testing the suit design in addition to the mobility aid design and all the other aspects that have to come together to make this happen. It's been an immense challenge for the SpaceX team.
And beyond just that, my understanding is that the suit is actually pressurizing to over 5 psi, which is actually quite high in terms of, I believe just the EMU was 4.5 or something, and I believe like the Apollo spacesuit was, I think below 4, like the A7. The A7L was below 4 psi, if I recall. So 5 psi brings up other technical challenges like mobility. Your joints get stiffer. The pressure difference between the inside of the spacesuit and outside, it just makes you more and more into a hard to maneuver inflatable arm thing. I can't even imagine. So what technical challenges? How did you come upon wanting to do 5 psi? What was the trade-off there, or what technology was unlocked that allowed for that increased mobility even at those higher pressure levels?
Yeah, well, I think first, give consideration, Gemini and Apollo, they were flying in 100% oxygen cabins. So they had already purged all of the nitrogen from their system before the EVA, in which case, sure, you would much rather have a lower pressure suit and gain back mobility and dexterity. Now, fortunate for us is that, 50, 60 years have transpired. So we can compensate by not having that 100% cabin environment by, doing a much more gradual pre-breathe to purge nitrogen from our system, but you still want that extra DCS protection. So running at a higher pressure helps counteract that and still retain some mobility, some dexterity by just 60 years of progress in, materials and joints. And that's, I mean, really, it's a lot of that credit goes right to SpaceX and all the talented people they've had working on this. It's been exactly as you've always observed them do in the world of building rockets, of test something, learn from it, and next week they'd do it totally different. We would leave SpaceX on a Friday saying, well, that suit seems okay, and then you come back Monday and you've got 2 new arms, and and it's a Frankenstein suit, but you're like, wow, that is so much better. And in fact, as we finally got in our flight suits, realized that, sometime, a couple months ago, they actually stopped rolling in some of the learnings into our training suits and just started rolling them into the flight suits. So like, instead of it being like a week by week graduation, when we put on our flight suits the first time, it was like, holy hell, this is like a huge step in the direction of progress. So hopefully that gives you some background on why we run it at the higher pressure. It's just really good for combating DCS, and also that they were able to do that and still gain lots of great ground in terms of mobility and dexterity.
That's amazing. So let's hear a little bit more about the suits, some of the cool features. Well, first of all, it's unbelievable. They look so similar to the standard SpaceX EVA suits. It's almost undistinguishable, really, from if you just kind of see the two side. If we don't see them side by side, I don't think I'd be able to pick up on the subtleties hardly. But some of the cool things, like it has a gold visor and lights and a heads-up display. It sounds like we could talk for an hour even just about the changes to the helmet. But why don't you give me a brief rundown on kind of what that looks like? Like, when does that day-night thing, does that all happen automatically? What's that? Is it a flippy thing? Like, whatever, whatever you can tell me.
I'll talk about the helmet.
I'll talk about the visor and then pass it off. Someone else can talk about a different aspect. The visor itself, it's a copper coating, and that's to provide protection, like a sunglasses, from harmful radiation. It's got ITO to protect or to retain the heat within the suit itself. There's an anti-fog coating as well, and it's impact resistance. It's actually the only visor that's been, it's a single layer. Relative to all the other spacesuits that's been developed. Visibility is great. One of the questions we've seen on X is like, does it impact, inside the capsule versus, outside protecting with the sun? No, it does not limit your visibility or acuity within the capsule. And then for us, sitting in the seat during the EVA, it gives us full range of visibility to execute our jobs as far as, being the eyes and ears for our crew members. So it's a really cool visor too.
Yeah, maybe going back a step to your broader question. SpaceX obviously started with the EVA suit, and we have some great technology there, and they said, okay, now what do we need to change to make a spacewalk possible? And I would say at this point, there is not a part of the suit that has not been modified. So while I agree it looks very similar, under the hood, it's almost entirely different.
Wow.
Really, like, there's not something at this point that hasn't been revisited from an architecture perspective. And when they started the process, they really started looking at manufacturing process. Like, how do we build a suit to start with that's more manufacturable? And what are the lessons we can learn as part of this that will allow us to someday scale the suits? So one of the big differences, for instance, just to start, is for our suits, they're actually now the entrance and exit is through a waist zipper that goes around the middle within the layers. So most of the EVA suits have an inseam zipper, and that's your ingress and egress path. It's now kind of relocated around the middle of the suit. There's a whole different patterning from the inside out for the restraint layer, the structural layers of the suit. It's an entirely different architecture to make sure you have mobility in the right spots. I think the joint development was a huge effort, as we've talked about a bit, but we only have room for one suit on this flight, right? So you have to design a suit that's both safe for people to be seated in seats with restraints over their shoulders. You can't have hard points that would interface with the straps. And so SpaceX has designed these really, really cool joints that when your suit is unpressurized, they're soft and flexible. And then when the suit pressurizes, they actually rigidize, and you still have the rotation in a number of different joints in your wrists and your shoulders and your upper arms that provide you the range of motion you need for moving and maneuvering your body. But that in of itself is just such a cool addition to the suits to enable this. What else, though? I mean, you've integrated an entire thermal layer into the suit. You now have to account for putting a person outside and giving them protection. We have this Pyron felt on the soles of the boots. That's actually what we use in like our thermal protection system on the spacecraft. So there's all sorts of thermal protection that's been added into this suit. I think there's parts of it that have like 15 different layers of material at certain points, because you have all of this MLI stacked up inside. That's, once you're at vacuum, then you have, you know, insulation layers that expand and give you thermal barrier. What else?
Yeah.
Oh yeah, I would say, so like start to stop on this. We had to ask the question of how do you add redundancy? You know, obviously we want to ensure we have as much fault tolerance as possible, and that kind of goes throughout the suit. So we now have redundant oxygen supply to the suit. So if you lose a feed, you can stay pressurized, get safely back in the spacecraft. The architecture of the seats has changed to supply that to crew members in pairs, so we can transition if anything were to happen. We have redundant, you know, visor seals to ensure that stays closed. There are redundant check valves in the suits. Kind of in every aspect, they went through and evaluated how do we ensure fault tolerance to keeping crews safe, and executing this with this suit architecture. So overall, it's been this incredible development effort by the suits team. I mean, huge shout out to the people that we work with every single day to test this and work with them, because man, it's just so inspiring to see what they're doing.
That's amazing. That heads-up display, then, is that, do you interface with that, or is it like a read-only type of thing that just kind of gives you a rundown on what your suit's up to, or does it also have mission stats and stuff? Like, what all is in that heads-up display there?
Yeah, so I mean, right now it gives us a lot of insight into the suit and some system health in like a color-coded way. But I think basically it's giving us the information that we need to know about our suit, and that it's trending well. So pressure, O2 timers, relative humidity, temperature. But it's not hard to see the direction it's going, right? I mean, this was another like example of leaving on a Friday and coming back Monday, and it was like we built a HUD, and it looked super ugly the first weekend. Like they just wanted to see if it made sense. It was like 3D printed, and then like you come back a week later and you're like, ooh, they made it look a little nicer. And then 2 weeks later, you're like, all right, it's flight ready. It's amazing. And it's not hard to see where they want to go with this, right? Like, I mean, this is an area where you could, you know, interface with augmented reality in the future, vehicle checklists. You know, it's
lasers.
Yeah, it's plumbed. I mean, it is like plumbed into the avionics of the vehicle. So the applications for it in the future is awesome, and I just love how it's like two SpaceX engineers a weekend and a pizza and what they can get done. I know, like our background with, you know, in aviation, we've tried to put HUDs in fighter jets, and it's like a 3-year project. SpaceX works on a little bit different timeline.
That's amazing. And I think lastly here, just remind us here, what's the actual, as far as the EVA, you know, timeline? Like, what's from hatch opening to hatch closing? How long is that? How many people are getting to actually poke their heads out? And yeah, just give me the full rundown on the actual EVA itself.
Sure. So the EVA operation itself will take about 2 hours. So that includes the time from the depressurization of the capsule, the time outdoors, and then the repressurization of the capsule as well. There will be 2 people going outdoors. It will be Jared and Sarah, and then 2 people supporting them from inside, being their eyes and ears, Kid and myself.
And are they going out simultaneously, or is it one and then the other?
One then the other.
Okay, that is good. And will all this be like, are you hoping to be able to stream the actual full EVA process and everything?
We will be. Yep, there will be 3 main live streams for this mission: the launch, the re-entry sequence, and then the EVA.
Amazing. And obviously people will be able to tune in on, you know, I assume on Polaris.com, or what's the best way?
I'd go to SpaceX.com.
SpaceX.com, and on X, it'll be on X there as well.
Yep, absolutely.
Yep. And of course, you guys do you have anything else special planned as far as fundraising and things like that? Anything else that you guys, I know you're continuing to work with St. Jude Children's Research Hospital. Anything else planned?
Yep, so we continue the mission to raise funds and awareness for St. Jude Children's Research Hospital on this mission, striving to add to the $250 million that was raised on Inspiration 4 and continue to make sure that we are not only moving human space flight forward for our collective future, but taking care of the now here on Earth to make people's lives better here too. And so one of the ways we're doing that on this mission is I actually co-authored a children's book with a woman named Carrie Vosek, and it was illustrated by Andy Harkness. And this children's book is all of our proceeds are going to St. Jude Children's Research Hospital. And it is the story of a mama dragon, and she journeys to space and shares it with her baby dragons back here on Earth. And it is the story of how love overcomes any distance. And I will read this to space to both my kids, who are ages 3 and 6, as well as some of the brave patients of St. Jude Children's Research Hospital. And then that unique space-flown copy will also be auctioned off after the mission to benefit St. Jude.
That's amazing. That's so cool. I mean, that has to be one of the coolest things. Wow. Okay, so, and lastly, I guess, then do we have an actual date? Was there a date on the calendar, or are we still just looking at kind of a rough time frame?
Well, first, I just want to add on, we have, in kind of furtherance of our important goal to support St. Jude, there is, as alluded to earlier, we do have a Starlink transmission that we've put a lot of thought into. We think is a very important opportunity to send a message to the world, and you can probably count that St. Jude would be part of it. So I would definitely say, stay tuned when we are on orbit. And in terms of our timing, I would say sometime the second half of June is looking pretty good. So.
That's coming up so quick. That is so exciting. Well, guys, I know you've got a lot of things going on and probably a million more questions to answer from everybody else. But on behalf of all of us spaceflight fans, I mean, this has been one of those journeys that we just can't wait, because we know how much hard work has gone on, behind the scenes, and so many little things that we don't even know about that you guys have been putting a lot of hard work into. But yeah, this is incredible. So we'll be cheering for you, and I'll hopefully try to make it out there for this launch and cheer you guys on as you go up into space.
Well, it'd be great to see you there. And by the way, our thanks back to you and everyone on your team. You're educating just millions of people and getting them excited about the future that we all want to live in someday. It's a really cool thing. So thanks for all your contributions to it, Tim.
Thank you very much. That means a lot. All right, Polaris Dawn, thank you guys so much. We'll be cheering for you. Can't wait for it.
Thank you.
Thank you.
Thank you.
Bye.
Thanks again to the crew of Polaris Dawn. I love talking to them. I feel like I always learn something new and exciting. So be sure you stay up to date with them on social media, or visit their website, polarisprogram.com/dawn. And I got to give a quick shout out to all of our supporters. If you want to support the work we do, head on over to patreon.com/everydayastronaut. That's going to do it for me. I'm Tim Dodd, the Everyday Astronaut, bringing space down to Earth for everyday people.